Okay, our last problem, excuse me, deals with the surface area of a sphere. And basically what we're going to do is we're going to prove something that we kind of already know geometrically. So if you think back to geometry, whoop, that's not good. Okay. Um, why is it doing that? There we go. All right, so if you think back to geometry, the volume of a sphere is given to us as 4/3 pi r cubed. And if you remember from calculus, ABBC, that if you took the derivative of the volume, bring the 3 down, multiply it, you get 4 pi r squared. And it just so happens that the derivative of volume is surface area. And really, if you think about it, that should make sense. Volume is a cubic. If you take the derivative of it, you're taking one dimension down into a two-dimensional, which is the surface area. So it's really not a coincidence that this works. And if you happen to remember, not that this really has anything to do with this problem, area of a circle is pi r squared. Take the derivative of the area of the circle, you get the circumference, which is 2 pi r. Again, not really a coincidence there. It works that way because this is two dimensions. Take the derivative, you're down to a one-dimensional figure. All right, but back to our circle. So this is what we're trying to show. We're trying to show that the surface area is this pi r squared. So what we've got is a sphere. Looks something like this. And something like that. So kind of a sphere. Looks more like an apple or something. Whatever. And on this sphere, from the center out to any point, is your radius. Well, we're going to call that radius. In this case, we're going to call it C. So C here is our radius. And I'm calling it C because we're going to have another R in the equation, and I don't want to get those two things confused. All right, so recall the surface area formula that we've learned is the double integral over D of the square root 1 plus the partial with respect to x squared, partial with respect to y squared, dA. So what we really need is we need an equation that we're going to be able to take the partials of x and y of this sphere. And we should know a pretty general equation for a sphere, which is x squared plus y squared plus z squared, assuming this is centered at the circle. I mean that this is centered at the origin. And that's going to equal our radius squared, which is c squared. That's the equation that we'll need to start with. All right, so to get our function from this, we need to solve it for z. So subtracting the x squared and y squared to both sides, we would get that z equals, if you got to take the square root, so it's the plus or minus square root of c squared minus x squared minus y squared. So we're going to need this because we need to find the partials of x and y. So we're going to take the partial of x, which is going to be, let's see, that's going to be all this to the 1/2. So it's 1/2 the inside, c squared minus x squared minus y squared to the negative 1/2 power, times the derivative of the inside with respect to x, which is negative 2x. And simplifying, that negative 2x times this 1/2 is going to give us a negative x over top of this thing right here, because the negative 1/2 power drops it to the bottom, so it's the square root of c squared minus x squared minus y squared. We'll have to do the same thing with y. hopefully you can see that y is going to give you the exact same thing. The only difference is you're going to have a negative y on top. So for the y part, I'm not going to write the whole thing out, but it would be negative y over square root of c squared minus x squared minus y squared. And then we need to square both of these because we're going to need the squares. So fx squared is going to be this thing here squared, which is nice because you square the top, square the bottom, and you're just going to get x squared over this thing, which is going to go away now, so it's over c squared minus x squared minus y squared. Let's make that a little bit better. There we go. And then fy squared, same idea. Square the top here, square the bottom, we get y squared over c squared minus x squared minus y squared. So then before I put all that stuff into the actual square root up here itself, I'm going to go ahead and add these two things together because I know it's going to be 1 plus the sum of this one plus this one. So I'm going to have x squared over c squared minus x squared minus y squared plus y squared over c squared minus x squared minus y squared. And that's going to be your fx squared plus fy squared portion. Obviously, I have a common denominator, which is good. So I'm going to combine these two things, and what I get is x squared plus y squared over the common denominator, which is c squared minus x squared minus y squared. But I know that this thing is a sphere, so it's going to be much easier to take this domain over polar. So I'm going to go ahead and convert this stuff right here to polar. So the nice thing is x squared plus y squared is r squared in polar. And this part, c squared, is going to be minus x squared minus y squared. Well, that's just negative r squared, so it's c squared minus r squared. So this is what we're going to need in terms of polar. So when I go ahead and set up this double integral to find the surface area is going to be the integral in polar. This thing right here goes all the way around. So the theta part is going to go from 0 to 2 pi. All right, the radius goes from 0 all the way out to the edge here, which we called c. And kind of going back to this piece right here, the positive square root of this is really the top half of the sphere, where the negative square root is the bottom half of the sphere. So if I only want to deal with the positive square root of this thing, I'm basically going to find the surface area for the top half. So I'm going to double my result here. So 2 times all of this. And so now I'm going to go ahead and plug in 1 plus this thing, because that was my fx squared plus fy squared, which is r squared over c squared minus r squared. And then remember that your conversion factor for polar was r dr d theta. And this is what we're going to go ahead and integrate. So let's see if I can do this. I'm not sure. We're going to try. Maybe. Let's see. Let's see if I can do it. Group. Let's group the whole thing. Oh, nice. Okay, so let's see if I can copy it. Ooh, I hope that worked. Let's find out. Try and copy it to the next page. Let's paste it here. Oops, not copy. Paste. Nice. Okay. All right. All right, I want to get rid of that. How do I get rid of you? Yeah, there we go. All right. So now let's go ahead and finish off the integral. In order to integrate this, we're going to need to combine what's underneath of here. So let's go ahead and do the algebra there. So we're going to have, oops, come on. We're going to have 2 integral 0 to 2 pi integral 0 to c. We need a common denominator. So this 1 is going to become c squared minus r over c squared minus r. R squared, excuse me. C squared minus r squared plus r squared over c squared minus r squared r dr d theta. Combining what's under here, if I combine the numerators now, the r squareds are going to go away. So that's going to leave us with square root c squared over c squared minus r squared r dr d theta. And then what you can do is you can take basically the square root of the top and the square root of the bottom separately. And I'm actually going to rewrite this. So let's see if you guys can follow this. If I take the square root of the top, it's just a constant, so it comes out as a c. So the c is going to go all the way out to the front. That leaves me with the square root of this thing, but it's in the denominator, so I'm going to write it as c squared minus r squared to the negative 1/2 times r dr d theta. All right, so in order to integrate this part, now we're going to do a little u substitution, where u is this thing right here, and it should get rid of this r. So u, come on, u is c squared minus r squared. So du is negative 2r dr. Solving for dr, we get that that would be du over negative 2r. So I've got 2c, integral from 0 to 2 pi, integral from 0 to c, of u to the negative 1/2 power r times du over negative 2r d theta. So the r's are going to cancel out. That negative 2 I can bring out here as a denominator, so it really just gives me a negative c, integral from 0 to 2 pi, integral from 0 to c. You know what? Let's change these bounds. So let's do the integral from, if I plug 0 into r, that's going to give me c squared. Oops, still an eraser, I guess. Yeah, so if I plug 0 in for r, that gives me c squared. If I plug c in for r, that gives me c squared minus c squared, which is 0. So then I'm going to have u to the negative 1/2 du d theta. And the good thing is, I can separate my u's and thetas. C is a constant. So all of this can be separated by Fubini's theorem. So really I can write this as negative c integral from 0 to 2 pi d theta times integral from c squared to 0 of u to the negative 1/2 du. So negative c, this one is going to be theta from 0 to 2 pi. This one here is going to be u to the 1/2 divided by 1/2 is multiplied by 2. So 2 u to the 1/2 from c squared to 0. So this is going to be 2 pi minus 0, which is 2 pi. So I get negative c, oops, that should be a c, negative c times 2 pi And this one is going to be 2 pi times 0 minus the square root of c squared, which is c. So 2 times minus c. So multiplying all this out, I get 2 times 2, which is 4. Pi negative c times negative c is positive c squared, where c was the radius, so 4 pi r squared is the surface area. There you have it.